So this talk is about my recent work with Shiken. He is a PhD student of the University of Tokyo who will graduate this September, and he will come to Minnesota Alexei place from this autumn. So, and the punchline of my talk is, so I'm discussing or revisiting the topological stability of solitons, and surprisingly, so yeah, so studying some exotic topological soliton, its topological stability is not fully characterized by homotopies. So homotopies still give us very important information to identify what kind of topological solitons exist. But if we carefully study the selection rule for discussing its stability, more complicated algebraic structure appears, and complete understanding of its symmetry can be, we have to use what is called as non-invertible symmetry. So after giving some brief introduction of the topological soliton, I will study in detail about the 4D CP1 sigma model, which can be regarded as various low energy effective theory of various theories such as 3+1D quantum antiferromagnet, or which can be also regarded as a low energy theory of SONCQCD with 2NF equal to flavor vector elements. And after giving some speculative remark of SONCQCD, I will summarize my talk. So let me give an introduction. So let's just consider some spontaneous symmetry rating from G to H, and assuming that G and H are both simply grouped. Then we have non-Goldstone bosons. So we are interested in what kind of low energy effective theory we can describe those non-Goldstone bosons. And we can conveniently describe them by considering the nonlinear sigma model whose target space is given by G divided by H. And summing up all possible configuration, we can describe that quantum partition function of the low energy effective theory. And if we just looking at the small fluctuation of this nonlinear sigma model, then we can study non-Goldstone boson, including its derivative interactions. But we can also consider about the large fluctuation, and they are topological solitons such as domain wall, vortex, hedgehog, and many interesting stuff. And how do we classify topological solitons? So nonlinear sigma model field can be regarded as a mapping from space-time to the target space. And in order to have topological soliton, we want to keep energy or energy density finite. That requires that, so we want to put the field at the boundary to point a specific direction in the target space. And this allows us to identify those infinities to the single point. So it's convenient to regard this spacetime as a sphere. So effectively, to classify topological solitons, so this nonlinear sigma model can be regarded as a mapping from sphere to the target space. And this naturally introduces the notion of the homotopy. And by looking at the homotopy, we can identify what kind of topological solitons exist in our low energy effective theory. Then the question is, what is the stability of the topological soliton? So we are interested in, for example, scattering experiment of various topological solitons. And do we get a trivial configuration in the end, or do we still get non-trivial soliton in the final stage? So those questions we would like to answer. And in order to answer them, we have to build up a selection rule or conservation rule for those topological solitons. And for that purpose, we have to identify what kind of symmetry is there that gives a selection rule for those topological solitons. And conventional wisdom is this homotopy group itself gives us those selection rule. So solitonic symmetry can be just classified by those homotopy groups. So this is a conventional wisdom. And we would like to, so I'd like to ask here, is this always true or not? And the simplest example, which is exotic, and that challenges this conventional wisdom, is this 4D CP1 sigma model. And as I said, so this can be regarded as some 3+1D quantum effective theory of 3+1D quantum system with spontaneous symmetry breaking pattern from SU2 symmetry down to its Maxwell-Arian subgroup U1. Then target space is given by this coset SU2 divided by U1, and this is what is called as CP1. Or equivalently, it is that just two sphere. But the description as CP1 turns out to be very convenient for later purpose, so let me briefly explain it. So for describing this coset, so we introduce two complex scalar fields and imposing the unit normal condition. So this makes a target space of this complex field as a 3-sphere. And we further introduce U1 gauge field and write down this Lagrangian. And since, because of this unit normal constraint, so this Lagrangian is completely quadratic in terms of the gauge field. So equation of motion of gauge field or path integral for gauge field can be performed exactly. And then, so A can be solved in terms of this Z. So in this sense, so A itself does not have any independent degrees of freedom. So this dynamics of A is completely determined from that of the complex scalar field Z. So in this sense, this auxiliary, this U1 gauge field is completely auxiliary. But for the purpose of introducing various operator, let me pretend as if we have a U1 gauge field A. And as I said, so I'm interested in various topological solitons of this 4D CPR model. So let me just restart the homotopies of the CP1 at low degrees. So it has no pi1, so there is no domain, there is no vortex, but there is a pi2, and there is a non-trivial pi3. And first, let me talk about the easier one, pi2, and after that, I will talk about the non-trivial consequence of pi3. So pi2, presence of pi2 describes the presence of the vortex soliton or one-dimensional higher version of the magnetic skimion in the condensed matter language. So pi2 of CP1, since CP1 is just two sphere, this is equivalent to G. And that suggests that there is some U1 conservation law. And indeed, you indeed have the Noether current described as a magnetic field in the language of the U1 gauge field. And the Bianchi identity for the magnetic field is nothing but the Noether's conservation law in this context. And this U1 symmetry is recently called as a U1 one-form symmetry. And the charged object for this symmetry is given by a magnetic line operator. So charged object is given by some line operator, and this is a line operator in 4 dimensions. So if I pick up this transverse plane, so this is actually the 3D space, and this intersection point of the line and this transverse plane is become a point, so you can surround it by 2 spheres. Then, so you can integrate this magnetic field over this 2 spheres, which measures the magnetic flux emitted from this point-like defect. So that means that, because of the Dirac quantization, this magnetic flux has to quantize to integer. So this means that, so this line operator is a world line of magnetic monopole in the 4-dimensional space-time. And so in high energy language, so this is nothing but a Tokuft line. And I will denote this Tokuft line as a V of V sub n, where the n is a magnetic flux. And to be precise, there is a more final classification of the vortex, but to speak about it, I have to first talk about the effect of pi3. So let me next talk about what is called Hoppion. So Hoppion is a non-trivial topological soliton related to pi3. So pi3 of CP1 or pi3 of CP2 is identical to integer. So that means that 3 sphere has a non-trivial winding on 2 sphere for integer times. And this follows from the what is called Hopf fibration in mathematical literature. So this says that 3 sphere can be regarded as a U1 bundle over 2 sphere. And we do not have to know about it in detail for this talk, but because of the naming of respecting this the work of Hopf, so topological soliton related to this pi3 of CP1 is called as Hoppion or Hopf soliton. And so pi3 of CP1 measures what is called as a Hopf number over 2 sphere, and And according to the seminar work by Wilczek and Z, so you can measure this pi3 of CP1 or Hopf number by integrating over Chern-Simons form over 3 sphere. So if we consider some point-like defect inside 4 dimension, you can surround it by 3 sphere. And if you integrate the Chern-Simons form of auxiliary U1 gauge field, it is quantized to pi times integer. And this integer is nothing but the measurement of pi3 of CP1. So this is what found by Wilczek and Z. So yeah, that's good. So we now have the meta charge for this pi3 of CP1. So that suggests that this integer conservation of Hopf soliton is the consequence of U1 symmetry with this meta charge.
Sorry. Why the Chern-Simons form integrate over S3s?
Yeah, so right. So even I think so for generic U1 gauge field, Chern-Simons form does not quantize at all. But in this case, since this U1 gauge field is constrained by this equation, and if you really integrate with substituting this expression, it turns out that this is quantized to integer. And a quick way to see it is if I take another derivative, it becomes dA square dA square, but there is no gauge invariant 4 form defined on 2 spheres, so it has to be 0. So there is no continuous deformation of this Chern-Simons form under this constraint. Yeah. Thank you for question. That's indeed a subtle point for this quantization. Okay, so since there is some meta charge, so we wanted to say that there is a U1 symmetry for this pi3 of CP1, but there is a subtle point. So although we now obtain a meta charge, then what is a meta current? So naively, we have to pick up the integrand as a meta current by this one. But you see, so there is a bare gauge field in the definition of the meta current. That means that this is not a gauge invariant, so it is not a physical observable. And a similar subtlety appears also in the case of the axial symmetry, axial anomaly for the QED, and I think Nabil will talk about it in tomorrow's part talk. So now the question is, do we really have a U1 symmetry without gauge invariant meta currents?
Can I ask a question about that? It's true that it's not gauge invariant, that guy,
yeah.
J-Hopf. It's also just not conserved, right? J-Hopf, the thing you wrote down there, because
so in this case, because this A is just a auxiliary field. This one, right. So in this case, this is conserved. Yeah. Okay. So it's a little bit different from that of the axial symmetry in this sense.
Right? You divide by 4 pi squared, no?
Right. So since here is pi, so I divide further by pi. Yeah. Okay. So now since we now got the knowledge about the Hopf number, so let me go back to the classification of the vortex operator. And this careful study of the vortex operator clarifies the more subtle issue related to the fact that this Hopf current is not gauge invariant. So in previous slide, I just defined the vortex operator as just a magnetic Truth line. But in order to make more precise definition, let me give a regularization of this vortex by removing the small neighborhood of this line, and we put the boundary condition on that boundary of this removed tabular neighborhood. And so that boundary is given by S2 times S1, and along with this S2, the A, so magnetic flux, is given by this quantized number N. But in order to classify the boundary condition of the sigma model field, we have to classify the homotopy of from the mapping from S2 times S1 to that target space CP1 with this constraint of the magnetic field. And this work has been done by old work by Pontiagin in 41, but in order to understand its physical picture more clearly, so it's better to ask what is the possible value of Hopf charge for this boundary condition of CP1 field over S2 times S1. And if you can define this Hopf number on this S2 times S1, we now get the final classification of vortex given by monopole charge in addition to Hopf number having this vortex operator. But there is a interesting subtle issue related to the gauge non-invariance of the Hopf charge. So this Hopf number for vortex operator is not well defined as integer, but it is well defined only modulo 2n. So there is no G classification for G final classification of vortex, but you still have G2n final classification for the vortex operator. And to see it, so let's try to evaluate Hopf number on S2 times S1, and in some specific choice of gauge, assume that you obtain some integer, say k. But this is not well defined because under large U1 gauge transformation along this S1, so this value of k is shifted by 2n given by this formula. So that means that so well defined value for k is only defined in modulo 2n, not integer, not in integer. And this subtlety is done by algorithm computation by Fontriagin. And one day she sent me this paper to me, and he just explained it to me. But embarrassingly, I couldn't understand it at all. And this way of understanding from the viewpoint of Chang-Science form would become clear, give the field theoretic understanding of what contrariety
Usually it's A by 2 pi.
A by 2 pi along this S1.
Why does the 4 pi squared becomes 1 over pi and not 1 over 2 pi?
So in order to do it correctly, so I have to take dA and take extension to 4D, and that gives subtle factor 2 here. And here I'm sloppy writing. I'm just sloppy. But if we do it correctly, we get factor 2. Okay. But so there is some subtlety for the definition of the Hopf charge for vortex, but what does it mean physically? And there is an interesting understanding by looking at the correlation function on a compact spacetime. So if we have symmetry, so correlation function on compact spacetime can be non-zero only if total charge is 0. So and this is the most basic fact coming out of the symmetry. And let's try to compute correlation function that only contains Hopf calculation or annihilation operator. And then this can be non-zero only if total charge is 0 in integer. And this suggests the presence of the U1 conservation law. But in addition, since we also have the defect operator as a vortex operator, so let's try to add it too. Then when does it non-zero? Does it become non-zero? Then it turns out that when this total Hopf charge is 0 modulo 2n, yeah, this can be non-zero. So whether or not it contains vortex line defect operator or not, so symmetry property seems to be completely different. So under the absence of this vortex operator, there is a U1 conservation symmetry. But if it contains vortex operator, then depending on its magnetic charge, yeah, you only get G2n conservation law. So is it quite weird? So
sorry, I just want to ask a question. I agree with you, it's very weird, but in the top picture, you measured the charge of HK3 by wrapping it with an S3.
Exactly, right.
Now, in the bottom one, though, you wrapped it with an S2 cross S1.
Yeah.
Now, but is it
so that point gives a subtlety. So what this means is that, so let's consider some vacuum which has a 0 Hopf charge and acts as this vortex operator.
Yeah.
And what would you get as a final state?
Yeah.
Then what you get is a mid state for all possible value of Hopf charge k modulo 2n. Right. So on torus, so it will define, it gives a specific value k modulo 2n.
Yeah.
But on the whole spacetime, so you have to define it as an integer, and what you get is a mixed state.
I see. So it's not, that's not, if I measure it with the naive S3 charge,
Yeah.
the lower one is not a charge eigenstate.
Right, exactly.
I see.
so it's quite surprising, right? And yeah, it takes several months for me to accept it, but yeah, this seems to be the result. But when we encounter the situation, what do you call it as a symmetrical? Is it U1, G2, G2, and what is the symmetrical? Yeah. And in order to get a clear answer to this question, so we have to generalize the notion of the symmetry. So conventional definition of the symmetry cannot capture the whole structure of the symmetry in this kind of subtle situation. And so we have to generalize our notion of the symmetry. And in recent context, so definition of the generalized symmetry is nothing but the data of the topological operator. And let me explain what does it mean. So let's just consider the usual continuous symmetry. Then you have a meta current, and you obtain the Modo-Takashi identity as a consequence of the local conservation law. And let me call it as a differential version of the Modo-Takashi identity. But there is an integrated version of the Modo-Takashi identity by considering the meta charge. So by picking up some dimension one subspace of the spacetime and integrating meta current on it, you obtain some meta charge. Then what's the consequence of the meta conservation law said is that, so if you compute correlation function including this meta charge, then under any continuous deformation of this submanifold, correlation function does not change at all. So this invariance of the of this meta charge operator under continuous deformation of submanifold is referred to as topological in the context. And this topologicalness of the meta charge is completely equivalent to the differential version of the Modo-Takashi identity. So, but for continuous symmetry, these two are just equivalent descriptions. So what do you gain from this rewriting of this one? So even in, for example, conventional symmetry, for example, if you have a discrete symmetry, you do not have a differential version of the Modo-Takashi identity. But for this integrated version, you can still construct some topological defect operator, and you can still write down the integrated version of the Modo-Takashi identity, even for discrete symmetry. So this already suggests that this integrated version is more useful to generalize the method of Modo-Takashi identity from continuous to discrete symmetry. And furthermore, so now people say that, okay, then if we have a topological operator that suggests some conservation law in your quantum field theory, then let's just accept it as a symmetry because it is as useful as conventional symmetry is. And according to this definition, so most ultimate form of the generalization is called as non-invertible symmetry, which is now in a huge fashion in this symmetry business. And that the name coming of non-invertible coming from the fact that so for this kind of symmetry defect, you cannot have an inverse operation at least in a local manner. So in that sense, there is a non-invertible operation, but captures the conservation law. Okay, then, okay, so it's okay to extend the notion of symmetry, and now the definition is given by the presence of the topological operator. But how do you find such topological operator if you do not have a recipe to create those unconventional symmetry? And recently, one of the good recipes is that just compare topological degree of freedom from outside of your world, and couple that topological degree of freedom to the dynamical degree of freedom without violating its topologicalness. Then you obtain topological defect operator. And if it acts non-trivially on your other local operator, then it gives the conservation law. So this is one of the recipes of constructing topological defect operator when you do not have a conventional technique to create it. And according to following this recipe, what we are doing here is consider some U1 Chern so bringing some U1 Chern theory or fractal quantum Hall state from outside of the world and couple it to this dynamical U1 gauge field of our theory and just to compute its partition function. And just call this partition function of topological field theory as a new symmetry generator. And it turns out that so this weird object is indeed captured the Hopf number charge in this in our case or for the CP1C1 model. Okay, so in order to check it, for example, let's compute this topological Chan-Simon theory partition function acting on this, for example, hop number operator, Hoppian generating operator. And so we put Hoppian generating operator surrounded by S3 and let's compute its partition function. And we have to perform path integral for Chan-Simon theory defined on 3 sphere. But for 3 sphere, so U1 gauge bundle is always trivial. So this path integral can be performed in a naive Gaussian way, and you obtain this original definition of the Hopf charge. And this suggests that so when we consider this kind of correlation function, this captures the Hopf charge correctly. And since this level n can be arbitrarily large number, so this charge k is effectively fixed as a value of the integer, not any modulo n. So this recovers the presence of the U1-like symmetry if correlation function only contains this kind of point-like defect operators. However, when vortex operator is present, the story becomes completely different. And so in order to see it, let's try to compute the action of this symmetry generator acting on vortex. Then what we find is since there is a vortex, so you have to surround it by S2 times S1, and let's compute the Chan-Simon partition function on S2 times S1. And now S2 times S1 has a non-trivial topology, so this path integral becomes a summation of a non-trivial bundle over S2 times S1. But punchline is, so since B also has a magnetic flux along this S2, and since it also has a holonomy along the S1, so you have to sum up all possible value of magnetic flux, and also you have to integrate over the holonomy. And if you perform this integration, then you find that, so if this level n does not match with this small n for the original definition of the magnetic charge, it just becomes 0. But only when this capital N and small n matches, you can obtain the Hopf charge of this vortex operator. So in this sense, so this weird topological quantum field theory partition function is intelligent enough not to try to diagonalize Hopf charge when this periodicity of the rotation does not match with the monopole charge. But if it matches, it captures the vortex Hopf charge of vortex operator correctly. So yeah, so the story turns out to be complicated, but the outcome is if we consider this weird topological field theory partition function, then you can correctly control the symmetry structure. And if symmetry looks like U1, it behaves as if it is U1 symmetry generator. But if symmetry turns out to be G2N because of the presence of vortex operator, then only when this rotation angle capital N matches with that G2 sub N, then yeah, it gives a non-trivial value. And if that it doesn't match, it just gives 0 and it refuses to give any charge of the topological Hopf charge of this system. Yeah. So yeah, there is a situation where for the CP1 model.
What was the? So what is the conclusion for the fact that so not every n is allowed in your opinion? Or what?
So yeah, all n is allowed. So all n is allowed for operators, but only when we have this situation, all n gives a non-trivial value. And for this kind of situation, that operator vanishes, and it is consistent with this G2 sub n conservation law. Yeah.
So what is the space of non-invertible symmetries?
Yeah, so at least so space of non-invertible symmetry contains all possible value of fractional topological field theories, and fusion rule becomes quite complicated.
Yeah.
And I cannot capture whole stuff, but at least for this kind of easy partition function, I can compute it to check its consistency. Yeah. Okay, so
And is it completely unrelated to the one-form symmetry? They're not intertwined into the two groups?
that's possible, but that part I still do not understand clearly. Yeah, honestly. Because so this dA is already can be regarded as a one-form symmetry generator. So in some sense, we already use the knowledge of one-form symmetry
So the
generator.
question is whether they're intertwined.
Yeah, right. Yeah, that one I still do not compute it. So yeah, I cannot answer at this moment. Yeah.
Also, like if you think about UV completions of this model, I would say this is accidental, right?
Yeah, this is accidental, right?
It's typically accidental.
Yeah.
But the one-form symmetry is robust.
That's true. That's true.
It suggests to me that it's a two group.
Yeah, maybe. Yeah, and from now I'm briefly talking about SONC QCD. Everything I will talk about is speculative, but maybe this has some application here. Okay, so right. So let me talk about its potential applicability of this weird symmetry to understand SONC QCD. So SONC QCD is a four-dimensional gauge theory with gauge group is given by orthogonal group, and let's add several left-handed masses Y fermion in the vector-like representation. And this has a chiral symmetry SUNF, but and when assuming that MC is large enough, broke linear condensate has Mondale vacuum expectation value, and this SUNF spontaneously broke down to SONF. And when NF is 2, this is exactly the situation where we have the CP1 sigma model as a low energy effective theory. And so, and this sigma model is the theory of meson given by this one, but in addition to this one, QCD also has the baryon operator given by this one. So not only this Kronecker delta, this epsilon tensor also gives a invariant tensor of SONC QCD. So these two are basic gauge invariant operators in this case. And the property of baryons, since it contains NC quarks, so baryons are very heavy. So typical mass of baryon is given by NC times some strong case. Okay, so it is roughly NC DEB. And selection or decay property of baryon is also quite interesting. If we collide two baryon, then outcome can become NC meson because the product of two epsilon tensor can be written as a sum of n product of n Kronecker delta. So just by this kinematic rule, so if two baryons collide, then final state can be NC meson, so baryon can completely disappear. And since these baryons are very heavy objects in the large NC limit, so it's natural to understand it as a topological soliton called skyrmions, and we want to understand its topological classification from homotopy. And if I consider pi3 of this target space, then when NF is 2, it gives integer because it's same with CP1. When NF is 3, it gives D4. And NF is larger than or equal to 4, it is D2. And this says that so baryon number symmetry is just D2. So low energy sigma model only reproduces the correct selection rule only when NF is large enough. So for small NF for 2 or 3, there is a discrepancy between UV and IR descriptions. And to my knowledge, so there is still no good control to understand or to mind the gap between this UV and IR description. And only good, only insightful study is given by paper by Imoto, Sakai's Imoto using the default. Yep.
Is it obvious that there should be an explanation in the effective field theory? Because what if the annihilation products are just not part of the EFT?
Right,
So
but
they're not both on both ends.
that's true. That's true. But then but still, so let's talk about the holographic setup which contains infinite power of heavy mesons. Yeah.
You must be. Can you explain to me simply why it's neat for two flavors? I must be.
So when NF is 2, so this is SU2 and this is SO2 is U1. So target space becomes CP1. So it's the same thing. And to answer Alexei's question, so let's consider holographic setup. So D4, D8, D8 with orient fold plane to make gauge group SON. And then so according to this holographic setup, this really reproduces G2 classification of the baryon number stability. But to explain it, so they have to use KO theory to explain its stability, which uses the pair creation annihilation difference. So even if you contain infinite power of heavy mesons, small fluctuation cannot capture this baryon instability of two baryon. So you still have to use the knowledge of very stringy non-perturbative phenomena to explain its G2 baryon instability.
Can you write down higher order term in the chiral function and then see the decay products?
So within meson theory, that's impossible. So for example, this kind of holographic setup is basically infinite power of, for example, hidden local symmetry. So basically it adds infinitely many interaction terms between mesons, but fluctuation or target space of this meson field itself does not capture this instability of two baryons, and you still have to use very non-perturbative phenomena within string theory. Of course, difference is also a dynamical object in string theory, so they can create annihilate, but yeah, it's quite tough to understand it from
But
field
this seems
theory.
like it fits with the perspective that it doesn't have an explanation in effective field theory, not even in the effective field.
Right.
The tower of states that are captured by supergravity. You need the full deep gradient.
Yeah, that's good. So, but this still suggests that we still have to take into account the effect of a stable confining string, since it is so center symmetry, even if there is no matter field, just G4 or G2 times G2. So for confining string can decay into it, and this kind of non-perturbative process has to be taken into account. So although it may not be a local field theory, but for example, suggestion of our computation is that Hopf number conservation can be explicitly violated by modulo 2 if we include vortex creation annihilation processes. And this kind of vortex may be understood as exactly as confining string. So maybe this kind of so although it is not a field theory, or so since this vortex is again a string theory, even in this description, but so this kind of deeper insight of Hopf number conservation may give a new scenario, may suggest a new scenario to understand, to get a better understanding of this
But
baryon.
we can also violate Hopfian conservation number by adding the Hopfian operator to the action.
Yeah, right.
It's even simpler than that.
Right, but just with that, so for example, pi2 of CP1 is an integer that suggests that confining string is also stable, not in modulo 4. It's stable.
You're saying that the effective field theory misses both the one-form symmetry,
Right.
and the Hopfian symmetry.
Exactly. And for example, if I use this vortex creation annihilation, both are
Yeah, you can
solved
see both
as
in one.
simultaneous. Right.
I assume
But-
that the very small loop is basically S squared or something, like a Hopfian squared.
I see. Yeah, it's
And the very
they
small loop is the
think
same
that-
as adding to the action a Hopfian squared.
Yeah, right. Yeah, so this part is completely speculative, so I do not have a complete picture yet, but I hope that this kind of study of linear symmetry may give a new insight to this for this kind of dynamical problem.
There is another problem that was
Yeah.
pointed out by Bolognesi about this.
Oh, I do not
Stefano
know.
Bolognesi.
Stefano, I see.
He computed the Wezomino width level, the chiral Lagrangian.
For SO case.
I don't remember,
Mhm.
but he actually found that there is a mismatch also in that.
Oh,
That
really?
Hopfians don't have the right quantum numbers to be variance.
I see. That sounds interesting. Yeah, could you tell me the paper later? Yeah, that sounds. Okay, so since it's up now, time is up, so let me summarize. So punchline of my result is topological conservation law of solitonic is not fully characterized by homotopies, and sometimes you have to use non-trivial topological quantum field theory partition function as a symmetry generator. Then this captures the whole story, at least for the case of CP1 sigma model. So solitonic stability of CP1 sigma model. And I'm not yet sure, but it may give a new insight for interesting application to the dynamics of SOQC. So that's everything. Thanks very much for your attention.
Go ahead, questions?
I had several, so I'm okay to other people ask first, but no one else is. Then. Could you give a physical, like, cartoon picture of what happens in the weird amplitude, like where these two, where the charge
Over this one?
laws, yeah, like
So for example, if I take this as a time axis,
Yeah.
then since this is a compact space-time, so by definition, final state has to be trivial or zero Hopf charge. So starting from zero Hopf charge, so acting in the vortex, it gives a mixed state 0, 2, 4, blah blah blah, and when depending on the number of Hopf charge as a inserted from the point like this. And since it is sandwiched in the vacuum state, so it picks up the specific state only when total Hopf charge is vanishing modulo to n. So when this vanishes in modulo to n, there is always a non-trivial amplitude because it creates all possible mixed state.
so the monopole string is like just creating an incoherent mixture of.
Yeah, right.
I think the reason why this is a disturbing picture to me is that I can imagine smoothly deforming the monopole string and collapsing it to 0, right? And then
So when this, so it depends on k. So for example, if this k is a non.
That's why I said that I think when it's very small, it's a Hopfian operator to the power n, to the power little n. That would explain this result. No?
Yeah, when k is 0, exactly. Yeah, I see.
you think that infinitesimally small monopole loop carries Hopfian charge. Is that?
Yeah, so when
That
k
seems
is
to
0, so
in the data.
Right. Yeah.
so it does not specify specific baryon number vector. So it
Okay.
is a mixed.
A sum over all different.
Yeah, right.
It's a sum over infinitely many that are divisible by little n or something.
Right.
That would also explain the chiral Lagrangian deformation that you need to edit.
Yeah, so that's my hope. Although I'm not really completely sure about it.
Okay. Very good. Thank you.
Right, next sheet.
Yeah, and for this flavor group,
This one? Yep.
That's one, yeah. It has also bosons with baryon charge, with quark charge. Is that correct?
No, so within Sigma model, so all methods have zero baryon charge.
SOQC?
In SOQCD.
I know, certainly this is true in normal QCD, but the SO.
No, I know it is true for two color QCD, but I also thought it was true for a joint QCD. But
You wrote the meson operators psi psi. you didn't put
Yeah,
bar.
right.
So doesn't it carry?
So since let's see. So this baryon number is not just given in the minus sign to the
Number is charge conjugation.
Yeah. So it's not non-trivial. Yeah, so this method doesn't have baryon charge, but this one has. So basically, it is flipping over all group. So
yeah,
charge conjugation.
so you have two different baryon charges actually, or quark charges.
Two
The
different-
quark number, the vessel sample CO quark number,
Okay.
and the baryon has the quark number has n quarks or n sync quarks.
Yeah. Yeah, right. But
But how do you count this for?
but Excel doesn't convert, so. But
But it's
yeah,
not well defined. right?
yeah,
It's not well defined. That's the issue. That was the objection to what I said.
yeah, it's not a conserved quantity, so yeah, in a snapshot we may count it, but it is, yeah.
Oh, so I also had a quick question.
Yeah,
So for the n equals 2 case, there is the sigma model has a 1-point symmetry.
Yeah,
It looks like it's a full-blown like U1, right?
right,
But then the UV theory has at most a Z2. right?
exactly.
Now, I guess I shouldn't be very surprised by that because the effective field theory may simply not capture screening and.
Right. That's
Is
true.
that, should I think about it that way?
Yeah, right. So that is the actual motivation adding vortex creation annihilation processes in this system. Then that process can violate U1 down to G2, right?
But that would strictly go outside the regime of AFT, right? So-
Yeah, that's true, that's true. Yeah, so I do not think this can be understood completely inside the field theory, but so I'd like to understand what is the minimal ingredient to be added to understand it. So that's a motivation for this part, but yeah, I know that part is not a controllable approximation, so this is just a model building to reproduce the QCD prediction. Yeah. Okay.